Okay, let's do a little bit more electrochemistry, and we're going to get crazy and see what kind of information we can get out of this here. And these are just a couple of standard potentials. I pulled them off the lab, and so you'll see that it's a little confusing. I had to think about it because that looks like the lead would not be happy to become a +2. But you got to remember these are all reduction potentials. And so it would be the lead ion becoming lead. And so what we can find is that when we have the negative, it's going to be more comfortable being the anode and getting rid of those electrons. So I'm going to write it like that. So Pb plus yields Pb plus 2 electrons, and then that's going to flip that over to be a plus 0.126. And then the silver, that's going to be Ag plus 1 electron yields Ag, and that's going to give me, okay, like that. Now, we see there, sorry that marker's not the best, I'll switch maybe. But so we see that we're going to have a viable circuit made here because it's going to be positive. And so 6 and 9 is 5, carry the 1, 12, carry the 1 again. That's going to be 0.925 volts. Now remember, it's important that we balance the electrons, but that potential is going to stay the same. So our potential is going to be 0.925 volts. But when I'm actually writing the equation, what I'm going to do is it's going to be 2 Ag plus 1 plus 2 electrons yields 2 Ag. Okay, and so that's going to be the truth there, because we need to cancel out those 2 electrons, and that's going to be important when I calculate the free energy. Delta G standard equals negative NF, and then I don't know what it is. I'm going to call it E again. I just don't know what it is. I could look it up, but I'm lazy and I'm old. And so I'm going to plug in N2. That's why it's important to balance those moles of electrons. And then 96,485, and that's coulombs per mole for the Faraday constant. And then the voltage is going to be 0.925 volts, and when you multiply all that mess together, you get joules. Okay, so it's going to be 2 times 96,485 times 0.925 equals 178,497 joules. Okay. And so that's going to be negative because there's a negative out in front of it. And so that's pretty easy. Now, we have talked about another formula here, and I just want to make sure that I'm going to get it exactly right. I'm pulling it up from my notes. I can find the K now that I have the G, and since my G's in joules rather than kilojoules, I'm ready to go. So my other formula that I can use is K equals E raised to the negative G standard over RT. Okay, so now that I've got the G standard, I can plug in the RT. The R is going to be 8.314 because it's a constant, and then since we're at standard, it's going to be 273. So what I have to remember to do is to put that negative, okay? So it's going to be negative 178,497 divided by 8.314 times 273, and that's going to be kind of a mess, but we'll be okay. So I find my E to the X button, That's shifted up from the natural log. And then I put in that I want a negative, and then I'm going to put in a parenthesis, negative 178,497 divided by, I'm going to do another parenthesis there, 8.314 times 273, paren, got to have two parentheses because I have parentheses within parentheses. Sounds like a Pink Floyd album. Okay, so I'm going to, this is what I have put into the calculator, and then with any luck, since we had that negative G, that's going to be a positive K. So I'm hitting equals, crossing my fingers. Oh yeah, woo, that's quite positive. Okay, 1.425, 1.43 times 10 to the 34th. And that's a big number, but I don't think that that's out of hand. I mean, I've seen other numbers. Particularly in class, we were doing those problems where we're combining reactions, and we would have numbers that big. So I'm going to go ahead and say that I didn't make a calculator error on that, and we did a really good job kind of getting a lot of information out of a little bit. So good job.